Let's talk about probability. So, probabilities are um, this notion of something being measured on this sample space. So we can talk about elementary events as possible outcomes of an experiment, and these elementary events live within a set which is called this sample space, and based on that we define probability as the likelihood of some kind of event taking place. So um, we can sort of talk about the axioms that go into uh, probability and sort of a probability distribution and what that means. And there are these three axioms that we need to keep in mind. So a probability distribution, which is the probability of some event happening. So let's say P of A, um, P of A, so the probability of event A taking place. This we can say is a probability distribution denoted P of A, the probability of A, with respect to some sample space. Let's say there's some sample space W, sample space, and this P of A is a function from events of W to real numbers following some axioms. So what are these axioms we have to follow? Well, first axiom is that for all events in W, so for all let's say M in W, subset of W, the probability of A, or the probability of M, probability of this event happening has to be at the very least 0. So it can't be negative. Probabilities have to be non-negative. The second axiom we have to follow is that the probability of W, which is the whole sample space, is equal to 1. So the probability of the entire sample space has to be 1. And the third sort of axiom we need to follow is for all, let's say we have two events, A and B, such that let's say we have these two events that are subsets of W. Now, I think we should use some more space here for all AB subsets of W. So that A intersection B equals empty set, or in other words, A and B are disjoint. If this is true, then this implies that the probability of their union, probability of A union B, is equal to probability of A plus probability of B. Probability of A plus probability of B. And hopefully you can see why if you took a look at the explanation of the rule of sum in the counting video, this must look a little familiar to you, and this is sort of intuitively true based on the same reasoning we applied in that counting video. So we have these three probability axioms that we talked about, and based on these three axioms, if we have some kind of P of A that follows these three axioms, we can say that P of A is a probability distribution. And also note that in that third example we just said, where A and B were disjoint and the union of A and B was the sum of their probabilities, the probability of their union was the sum of their individual probabilities. That can be applied to more than just two events, right? So that can be maybe 3, 4, indefinite number of events. And if you union all of them, and that would be the same as the probability of their individual sums, or sorry, the sum of their individual probabilities. And based on those few axioms we just had, we can also talk about a few corollaries. So there are a few things that follow, few properties that follow from those axioms, and one was probability of the empty set is equal to 0. So the event, which is the empty set, always has the probability 0. Now, another property is that for any A and B that are subsets of our sample space, we have that whenever A is a subset of B, we observe that the probability of A will be lesser or equal than the probability of B. And once again, this shouldn't be too surprising. Everything in A is in B, so the chance of the likelihood of event A should not exceed the likelihood of event B, right? This is all it's saying, which sort of makes sense. So another thing we can observe is that for any event A in the sample space, we have that probability of everything else in the sample space except for A is equal to probability of A complement, and A complement is precisely everything that's in the sample space except for A, which is not in A. And this is equal to 1 minus the probability of A. And this is often an important result that we can use for various problems, and it's a nice corollary that we see from those axioms we originally had. So one last corollary we will talk about is the probability of, or I should say, for any AB that are events in the sample space, the probability of their union, probability A union B, is equal to probability of A plus probability of B minus the probability of their intersection, because you don't want to double count the elements you already counted in B or A. So you will have to remove the intersection at one time, just not to double count those intersection probability, that intersection probability. And that's why that's sort of the idea. You just want to avoid double counting probabilities of the intersection, because P and B may have common elements, right? So this also shouldn't be surprising, and we can say we can clearly see that if the intersection was the empty set, right? Then based on the first corollary we talked about, this probability is 0. And if this is the empty set, this is precisely, by definition, two disjoint sets. And we see that axiom 1 holds, or sorry, axiom 3 holds, because axiom 3 says whenever we have two disjoint sets, A and B, the probability of A union B is the sum of their individual probabilities. So it's nice that it is closely tied with that axiom, we can see.